All right. 4.2, some probability rules. We're talking about or rather not conditional probabilities, but compound events. A compound event is, unlike the previous probabilities, in which there are multiple things going on. So one compound event would be the independent versus dependent events. If they're independent, you've got two outcomes that are separate from each other that can occur, and one probability doesn't affect the other. Dependent is when you have two outcomes or more outcomes of an event that occur, but now the outcome of one affected the outcome of the other. Either way, you're going to end up multiplying these probabilities together, these two or three different probabilities. Okay, so independent events, two events are independent if the outcome or non-occurrence of one event does not change the probability of the other event. The rule for multiplication or for independent events is that you're going to multiply the two events together. The probability of A and B is equal to the probability of A on its own times the probability of B on its own. For an example, we flip a coin twice. These outcomes are independent because the first flip doesn't affect the second flip. So the probability of getting heads on both flips would be probability of heads on the first flip, which is 1/2, times the probability of getting the heads on the second flip, which is also 1/2. So 1/2 times 1/2 is 1/4. Okay, conditional probabilities. If events are dependent, the occurrence of one event changes the probability of the other. So the probability of P parentheses A/B, that slash means given. So it's read as the probability of A given B. The probability of A comma given B just means about the same thing. It's just talking about the notation, how they go about writing it. So in a 52 card deck, we've got 8 cards given hearts. So that means that I'm only worried about not the 52 cards, but the 13 of them that are hearts. And how many of those 13 are hearts? 1. Probability of face card given that are red. There's 26 red cards, and I believe there are 6 face cards that are now red too. So your ace, king, jack of hearts, and ace, king, jack of diamonds. Sorry, not ace. King, queen, jack of hearts, and king, queen, jack of diamonds. So here we go. Dependent events, you're still going to multiply the probabilities. You're just dealing with a conditional probability piece into that. So here we go. When choosing 2 cards without replacement, okay, I'm going to take and find the probability of getting 2 5s. Are these two independent or dependent? And because we're not replacing the card, they're dependent. Because my first card has a 50 out of 52 chance of getting drawn, the second one has an out of 51 chance of getting drawn. In fact, not only does the denominator in my fractions change, but my top went from 4 cards down to 3 because there's fewer of those cards in the deck. Now let's do the same pretty much experiment, but we're going to put the cards from 2 separate decks, which is now going to make them independent because I have a 4 out of 52 chance of getting the first 5. I've got a 4 out of 52 chance of getting the second 5. So multiply it together to get 1 out of 169. But now it's independent because the first draw didn't affect the probability of the second draw. A couple of things. When we're dealing with OR, we're talking about one event and one draw, one roll, one flip, etc. The word and means something different. The word and means in Venn diagram where those two characteristics happen at the same time. Okay. Some notation for you that I won't necessarily use, but maybe you'll come across it. If you see A with a U and then B, that's A union B. A or B means either A or B occurs, or both A and B occur at the same time. So that's pretty much everything. The upside down U means intersection. That means we're interested in the grouping where they overlap. Okay, so I talk about mutually exclusive. I might say on the other end of that, overlapping, where overlapping means the actual circles, the Venn diagrams would overlap each other. Mutually exclusive, they're not going to touch each other. So that means A and B cannot happen at the same time. You can think of mutually exclusive versus not mutually exclusive is the same formula. There should be a minus in there. Either way, when it's or, you're going to end up adding the probability of those two. Okay. Now, sometimes you have to subtract the number because they counted the number twice, but that's not the case for mutually exclusive. It's the not mutually exclusive. And here, maybe an example will help out with that. For example, I've got the probability of getting a heart or a face card. So I can take the probability of heart, and I'm going to add it to the probability of FC for face card. There are 13 hearts out of the 52, added with the 12 face cards out of 52. But the only problem is I have 3 cards that are shared in both Venn diagrams. So I'm going to have to take away the probability of them being heart and face card at the same time. That's not the same end as before. That's just meaning they have the same characteristic. Okay, work that out, and I end up getting roughly like 22 out of 52. Now, I would reduce that later, but for the sake of time, I'm not going to reduce it right now. Okay, so these are not mutually exclusive because they can occur at the same time. Whereas the probability of ace or face card, I can take the probability of ace, and I can add to the probability of face card, but I don't have to subtract anything because if you notice, the 2 circles have nothing in common. So I can just take the 4 aces and add it to the 12 face cards and get 16 out of 50. Okay, like I said, you should reduce those, but I'm not going to do that for the sake of time. Contingency table is just a way of putting in information in this table. In fact, it's got a grand total of 187 people in the table. We have for males the 54 that went to and graduated from college. We've got for 31 that didn't. So add them together, you get 85 males. 62 females and the 40 females add up to 102. These two are going to add up to 187. Okay. Or if I'm looking at a college graduate row, the 54 college graduates plus the 62 graduates is 116. The non-graduates, the 31 plus the 40 adds up to 70. So in my contingency table, that's going to help me out when I'm asking certain things. Like, for example, the probability of male and college. So I'm going to go to male and college, and I'm going to have a 54 out of 187. Okay. 187 because we're asking out of the entire population. Male or college. So now I'm going to grab the 85 that are the males, and I'm going to add it to the 116 that graduated from college. But now this 54 got counted twice, so I'm going to have to take away the 54. So real quick, 85 plus 116 minus 54. I got 147 out of a grand total of 187. Male given college graduates. So now I'm only interested in the college graduates. That's what that conditional probability does. It's cutting it down to 116. And of those, there's 54 males. So that's 54 out of 116. This is the first time that your denominator changes because of the given piece of that. Okay, here we go. Got a set of homework problems to look at and do. A lot of them, I believe, well, actually all of them are odd. So go through and run through as many of those as possible.